Hello and welcome to the YouTube channel D Creations Resources. We are looking at different concepts from science, especially physics and maths, and even some things in languages as well. Well, now since the few episodes we have been talking about vibrational spectroscopy, and we discussed several aspects such as an electromagnetic radiation, what spectroscopy means. Then we discussed about different regions in the electromagnetic spectrum, of course emphasizing on infrared radiation because we know that it's associated with the vibrations. And right now let us start talking about infrared spectroscopy. Now, we have seen how functional groups are determined in infrared spectroscopy, and one important aspect to note about this particular technique is that you can analyze a sample in any state, in the sense that the sample could be liquid, or it could be a paste, it could be a powder, it could be a film, and it could even be in gaseous form, or it could be in solutions or fibers or surfaces, and it can still be examined using this particular technique. All you need to do is you have to make a judicious choice. So there could be a different kind of an assembly for a certain kind of or the certain state of the sample, so you need to choose that. Now, infrared spectrometers have been around since a long time, like around 1940s. Commercial infrared spectrometers were made available, and earlier the dispersive element was the prism. So as you know, dispersive element plays an important role in an infrared spectrometer. So that time it used to be prisms. Then of course there was development in the technology, and monochromators were developed. Now, one thing one needs to know, although we said that a sample in any state can be analyzed by infrared spectroscopy, not all samples can be analyzed by infrared spectroscopy. In fact, this is one of the disadvantages, you can say. The reason being that since infrared spectroscopy is sensitive to the presence of functional groups in a sample needs to contain chemical bonds to have an infrared spectrum. So if you consider single atomic entities, they contain no chemical bonds. So obviously you will not be able to get any kind of infrared radiation absorbance there. So atoms or monoatomic ions will not have an infrared spectra, or noble gases such as helium and argon are not going to have an infrared spectra, because we know that they are noble gases and they exist as individual atoms. Even if you consider monoatomic ions dissolved in water, for example lead Pb plus 2 ion dissolved in water, it is not chemically bonded to anything, and so even it will not have an infrared spectrum. So if you are trying to, for example, analyze drinking water for the presence of lead, then you cannot choose infrared spectroscopy for that. You need to use some other techniques. So basically, it is not possible for infrared spectroscopy to give you a result regarding the measurement of level of an element in a substance unless the element is present as a part of a molecule whose spectrum can be detected. Now you might wonder that, okay, fine, it doesn't give infrared spectrum for single atoms. What about molecules? Do all molecules give infrared absorbance? Well, no. All the molecules also do not absorb infrared radiation. Especially the homonuclear diatomic molecules do not absorb infrared radiations. Now, when I say homonuclear diatomic molecules, that means there are two identical atoms. For example, N triple bond N or O double bond A. So these do not possess infrared spectra because they are symmetric in nature. So if you want to determine the amount of nitrogen or oxygen in ambient air, there's no point in using infrared spectroscopy there. So you can even classify the molecules as being IR active, that is infrared active, and IR inactive. And in determining which of them are IR active and which of them are IR inactive, one important term that you need to know about, or one important concept that you need to keep in mind, is that of dipole moment. So a dipole is means relate to two, and pole is related to charges. So two opposite charges separated by a distance. That is a dipole. What is a dipole moment? So for a simple dipole, the dipole moment is the magnitude of either charge in the dipole multiplied by the charge spacing. So if there are two charges, say Q plus and Q minus, which are separated by a distance d, and the magnitude in both the cases for the charges is Q. So the dipole moment will be Qd. Now what if the molecule is complex? In a complex molecule, you imagine that there's a positive particle representing the total positive charge of the protons concentrated at the center of gravity of the protons, and the negative particle represents the total negative charge of the electrons concentrated at the center of gravity of the electrons. So since the wavelength of infrared radiation is much greater than the size of most of the molecules, the electric field of the photon in the vicinity of a molecule can be considered uniform over the whole molecule. Now the electric field of the photon exerts forces on the molecular charges, and by definition the forces on opposite charges will be exerted in opposite directions. Therefore, the oscillating electric field of the photon, so when I'm saying photon, basically we are referring to the electromagnetic wave, right? We know that in particle form it can be represented by a photon. So it will exert forces tending to induce the dipole moment of the molecule to oscillate at the frequency of the photon. Now at certain frequencies, the dipole moment and the nuclei oscillate simultaneously. So these are molecular vibrational frequencies where the vibration results in a change in dipole moment. So at such a frequency, a forced dipole moment oscillation will tend to activate a nuclear vibration, and the more the dipole moment changes during a vibration, the more easily the photon electric field can activate that vibration. So if a molecular vibration should cause no change in dipole moment, then a forced dipole moment oscillation cannot activate that vibration. So basically this leads to a selection rule that in order to absorb infrared radiation, a molecular vibration must cause a change in the dipole moment of the molecule. So the change in dipole moment of the molecule is very, very important. In fact, the square of the change in dipole moment caused by the molecular vibration, which is giving rise to the absorption band, is what the intensity of an infrared absorption band is proportional to. So basically the intensity of an absorption band is proportional to the square of the change in dipole moment. So in a diatomic molecule, the two atoms are vibrating back and forth about the mean position in opposite directions, and of course simultaneously at the same time. Now the frequency of these vibrations, of course, is called a stretching frequency, and here if you can recall what a simple harmonic oscillator is, here they are behaving like a simple harmonic oscillator. And coming back to the selection rule, we said, what has to be the selection rule? The criteria for a molecule to show infrared spectrum is there has to be a change in the dipole moment of the molecule during the vibration of the molecule. So now if you consider homonuclear diatomic molecules, say H2, Cl2, N2, O2, etc., will they have any permanent dipole moment? No. And in fact, even stretching of the atoms about the bond is not going to give rise to any dipole moment. So homonuclear diatomic molecules are IR inactive. We've already said it earlier, but I'm just repeating it. But if you consider the case of heteronuclear diatomic molecules, so homo, as you know, is similar and hetero is different. So what could be an example of a simplest molecule? Carbon monoxide or HCl for that matter. They possess a dipole moment, and that's why both these molecules are IR active. Okay, and of course the dipole moment will change when the bond length changes, because you know that it is proportional to the distance between the two charges. So that will change, but we are interested right now in the change in the dipole moment itself. So given, say, four molecules, say H2, N2, CO and HCl. Two of these are IR inactive, namely H2 and N2, and two of these are IR active, namely carbon monoxide and hydrogen chloride. HCl or carbon monoxide is CO.